Good day everyone. Welcome to Unit 4, Lecture 1 for CpE2301 Logic Circuits and Design. Unit 4 is all about bistable elements in clocked synchronous sequential circuits. Unit 3 covers the following topics: Introduction to sequential circuits, latches and flip-flops, flip-flop characteristic tables and state equations, the 7475 quad bistable latch, the 7476 dual JK flip-flop, analysis of sequential circuits, flip-flop excitation tables, design of sequential circuits, state reduction and assignment, sequence detector circuits, design with unused states, and design of counters. For this discussion, we will focus on the introduction to sequential circuits and latches. To start our discussion, let us recall the basic differences between combinational circuits and sequential circuits as mentioned in Unit 3. We have here a block diagram of a combinational circuit. As discussed in Unit 3, combinational circuits consists of logic gates whose outputs at any time are determined from only the present combination of inputs. This means that the outputs of the entire combinational circuit, as well as the outputs of the internal gates, can be obtained at any instance of time for as long as we know the input combinations at that same instance. For a sequential circuit, on the other hand, it is similar to a combinational circuit as seen here, where there is a combinational circuit that accepts inputs and generates outputs. However, the difference between combinational circuits and sequential circuits is here, where there are memory elements involved in the circuit. These memory elements take inputs from the combinational circuit and generates outputs that are used as feedback inputs to the combinational circuit. So unlike that of a combinational circuit, in a sequential circuit, knowing simply the inputs does not guarantee that you will be able to know the corresponding outputs, since there are internal inputs, outputs, and state that you need to consider. In this unit, we will explore how these memory elements function in sequential circuits and how they are designed and implemented. To start our discussion, let us formally define a sequential circuit and look at its characteristics and different types. A sequential circuit is specified by a time sequence of inputs, outputs, and internal states. In contrast, the outputs of combinational logic depends only on the present values of inputs. The outputs and next state of a sequential circuit is a function of both inputs and present state. A state refers to the binary information stored in the storage elements. State may refer to the past value of a memory element, the present value it currently holds, or the next value it may hold. This will be explained more later. Sequential circuits are generally classified into two types: synchronous and asynchronous. Synchronous sequential circuit is a system whose behavior can be defined from the knowledge of its signals at discrete instants of time. It means that the state of the circuit only changes at discrete times in response to a clock signal. in the form of pulses provided by a clock generator. The synchronous sequential circuit is dependent upon the clock timing element in executing some of its operations. On the other hand, a synchronous sequential circuit depends upon the input signals at any instant of time and the order in which the inputs change. It means that the state of the device can change at any time in response to changing inputs and internal states without regard to the clock signal. The asynchronous sequential circuit is not dependent upon the clock timing element in executing some of its operations. Here we have some terms that are associated with sequential circuits. First is clock generator. A clock generator is a timing device used by a sequential circuit for synchronization. It is responsible for providing a sequential circuit. The second item here, which are clock pulses. Clock pulses are often called just clock or CLK. Clock signals come from clock generators in the form of periodic train. This means that the signal is made up of a series of oscillating values of ones and zeros. For the third item here, clock sequential circuits. These are synchronous sequential circuits that use clock pulses provided by clock generators to control the storage element or elements of the circuit. And lastly, flip-flop. This is a term used to refer to the storage or memory elements used in clock sequential circuits. A flip-flop is a binary storage device capable of storing one bit of information. Now let us look at again the diagram of a sequential circuit and see how these terms are associated to it. In this illustration of a sequential circuit, we can see that the memory elements are also called flip-flops. There is also another type of storage element called latch. The two shall be explained further later. These memory elements are provided clock pulses for synchronization, and these clock pulses are coming from a clock generator. The clock pulses are in the form of a periodic train or a series of oscillating values of ones and zeros, and may look like this, where the low value of the graph is 0 and the high value of the graph is 1. Flip-flops are often regarded to as bistable elements. Bistable elements are circuits with two stable states, 1 and 0. This means that the output of the circuit, in this case a flip-flop, can be 1 or 0, and it is capable of keeping that output value or state indefinitely until something causes it to change its output value or state. The output value or state mentioned here is what's stored in the flip-flop as a memory element. Let us now analyze how a bistable element works. Let's start our analysis with a NOT gate. If we construct a NOT gate circuit in this manner, where the output is connected as feedback to the input, the behavior of the NOT gate will look like this. The output will keep on oscillating between 0 and 1 with respect to time, as shown in this graph. This behavior shows that the NOT gate output is unstable since it cannot keep an output value or state of 1 or 0 for an indefinite amount of time since it keeps on changing. This behavior is not something we want for a bistable element or a flip-flop. In order to keep its output value or state indefinitely, we can modify the NOT gate circuit and create something like this. The two circuits set up for the NOT gate here are now capable of holding an output value or state indefinitely. You can see that if we cascade two NOT gates in this manner and treat this end as output, which is 0 in this example, and use it as feedback input here, the output on this end will remain the same, which is still 0. This is also true on this other circuit, where 1 is considered the circuit output on this end and used as a feedback input here. You will see that the output on this end will remain the same as the previous output. For both of these cases, the output value or state of the circuit remains the same indefinitely. The behavior is what we want for a bistable element. We can redraw this circuit and it will look something like this. For this part of the discussion, let's label the circuit according to these names. Here we are labeling and treating the inputs and outputs of the gates as voltages, because we have to remember that although gates are primarily used with logic levels like 1 or 0, but they can also be treated as voltage levels. Here, Vin1 is the input voltage to this NOT gate, which is equal to Vout2, or the output voltage of this NOT gate. On the other hand, Vin2 is the input voltage to this NOT gate, which is equal to Vout1, or the output voltage of this NOT gate. We also label the outputs of the two NOT gates as Q and Q prime respectively. They will always be complements of one another and will never have the same logic values due to the setup of the circuit. This diagram will show us the behavior of the circuit with regards to the input or output voltages. We can see that when Vout1 or Vin2 is logic 1, or approximately 5 volts, Vin1 or Vout2 is logic 0, or approximately 0 volts. This is considered a stable state, and the circuit is capable of holding this state indefinitely. When Vout1 or Vin2 decreases and approaches 0 volts, or logic 0, as shown by these graphs, it can be seen that the state passes through a metastable state, and that Vin1 and Vout2 approaches 5 volts, or logic 1, which is also a stable state, and the circuit is also capable of holding this state indefinitely. If we look at it the other way around, we can see that when Vout2 or V-in1 is logic 1 or approximately 5 volts. V-in2 or Vout1 is logic 0 or approximately 0 volts. This is considered a stable state, and the circuit is capable of holding this state indefinitely. When Vout2 or Vin1 decreases and approaches 0 volts or logic 0, as shown by these graphs, it can be seen that the state passes through a metastable state, and that Vin2 or Vout1 approaches 5 volts or logic 1, which is also another stable state of the circuit, and the circuit is again capable of holding this state indefinitely. Here we can see that overall, these kinds of circuits may go through a metastable state, which is a state neither of the two stable states, 1 or 0. They go through the state when shifting from one stable state to another. As seen in this diagram, when a bistable elements are in a metastable state, it is like being a ball in a steep hill. Slight variations on voltage levels between states may tend to automatically pull the bistable element to either of the two stable states, 1 or 0, or vice versa. As mentioned earlier, a storage element in a digital circuit may maintain a binary state indefinitely, as long as power is delivered to the circuit, until directed by an input signal to it to switch states. The difference among storage elements mostly are according to the number of inputs and the manner in which the inputs affect the binary state. These shall be discussed more in later discussions. It was also mentioned earlier in the discussion that flip-flops and latches are two types of storage or memory elements, but between the two, flip-flops are more commonly used in sequential circuits. Latches are storage elements that operate with signal levels. This means that they are level sensitive. They are not practical for use in synchronous sequential circuits. Take note of the term level sensitive, as we will explain it further in a while. Flip-flops are storage elements controlled by a clock transition. This means that they are edge sensitive. Take note as well of the term edge sensitive, as we will explain it further in a while. Remember that as storage elements or memory elements, both latches and flip-flops are capable of storing one bit of information given by its output value or state. Now, going back to the level sensitive and edge sensitive characteristic of latches and flip-flops respectively. Latches are generally level sensitive. This means that when considering clock input signals, they operate and are triggered using either of the logic levels 1 or 0. Each latch will have its own specific level of sensitivity. Flip-flops, on the other hand, are generally edge sensitive. This means that when considering clock input signals, they operate and are triggered using either of the edges in the signal. It could either be the rising edge or positive edge, or the transition from 0 to 1. or the falling edge or negative edge, which is the transition from 1 to 0. Each flip-flop will have its own specific edge sensitivity. In circuit analysis, one useful tool that can be used is a timing diagram. A digital timing diagram is a representation of a set of signals in the time domain. It is used to graphically show the operation of various circuits and is considered a graphical truth table. Here, for example, we have an AND gate with inputs A and B and output F. The timing diagram here shows all the possible combinations and behavior of the inputs and output using graphs of ones and zeros with respect to time. As you can see, at the first time instance here, it is shown that when an input of A is equal to 0 and B is equal to 0 is considered, an output of F is equal to 0 can be obtained. At the next instance of time, it is shown that when an input of A is equal to 1 and B is equal to 0 is considered, an output of F is equal to 0 can be obtained. This may be continued following the truth table of the function to show other possible input-output scenarios, as seen here. Here we also have another example using a function f is equal to a XOR b XOR c. A, B, and C are the inputs and F is the output. In the timing diagram here, we can also see all possible combinations and behavior of the inputs and output using graphs of ones and zeros with respect to time. Like the previous example, it can be seen here as well that various input-output scenarios of the function show various are shown in various instances of time. Let us now discuss latches. Latches, as mentioned earlier, are also storage or memory elements. They are considered the building blocks of flip-flops. There are generally two types of latches. The SR latch, which can be implemented using NOR gates or NAND gates, and we also have the D latch. Let us now discuss how these latches are constructed and implemented. We start by going back to the cascaded NOT gates we had in the discussion earlier, as shown here. If you can recall, NOT gates can be implemented using NOR and NAND gates by shorting together their two inputs to have a single input only. So therefore, this circuit can now become like this. We have this circuit with the NOT gates implemented using NOR gates, and this circuit with the NOT gates implemented using NAND gates. These two circuits will behave in exactly the same manner as this circuit, where they can hold an output value or state indefinitely. If you notice, the circuit is a closed loop. Once it is functional, we cannot introduce inputs to it to possibly change its output. Now, What if we modify these circuits a bit so that we can introduce inputs to them to vary their outputs? We can do that by disconnecting the shorted inputs to the NOR and NAND gates. The circuit will now become like this. You can now see that the two circuit implementations can now accept inputs. With that, we can already vary their outputs and influence its storage and memory characteristics. These two circuits are now the basic implementations of an SR latch. SR latch using NOR gates and SR latch using NAND gates. Let's discuss the characteristics of an SR latch using the NOR gates. An SR latch implemented using NOR gates have this as the R input and this as the S input. This is the Q output and this is the Q prime output. Take note of the assignments of the inputs and outputs as they cannot be interchanged. This here represents the block diagram of an SR latch using NOR gates. Let's now try to see how the latch behaves using this truth table. Let's examine its behavior according to each input-output combination. In the truth table, note that S and R are the current inputs, Q is the current output, Q prime is just not included in this illustration and discussion since it can be easily obtained as a complement of Q. Q next is the next value of the output Q after considering the present values of the inputs S and R and the present value of the output Q. Q next prime is simply just the complement of Q next. Let's now see the behavior of this SR latch according to the first set of input combination. We shall consider these two input-output combinations together since they have the same behavior. Here, we can see that when the present SR inputs are 0, 0, the next value of Q as given by Q next will not change based on its present value as seen here. 0 will remain 0 and 1 will remain 1. This behavior of the SR latch is called no change since the present value of Q does not change on its next value. Q next prime is simply the complement of Q next. Here, we can see that when the present inputs of S and R are 0 and 1, the next value of Q will always be 0, regardless of its present value as shown here by X. If Q is 0, Q next will remain 0. If Q is 1, Q next will become 0. This behavior of the SR latch is called reset, since the present value of Q is always reset to 0 on its next value. Q next prime is simply the complement of Q next for this input-output behavior. Here, you can see that when the present SR inputs are 1 and 0, the next value of Q will always be 1, regardless of its present value as shown here by X. If Q is 0, Q next will become 1. If Q is 1, it will remain 1. This behavior of the SR latch is called set, since the present value of Q is always set to 1 on its next value. Q next prime is simply the complement of Q next. Here, we can see that when SR inputs are 1, 1, the next value of Q will always be 0, but so as Q next prime. This will happen regardless of the present value of Q. Remember earlier in the discussion, it was mentioned that these two should never be the same. But in this case, both are 0. That is why this is considered an invalid or indeterminate behavior for an SR latch. The reason why this latch is called an SR latch is because of the set and reset operations that it performs. Let's now discuss the characteristics of an SR latch using NAND gates. An SR latch implemented using NAND gates have this as the S prime input and this as the R prime input. Take note that for this SR implementation, the inputs are complemented. This is the Q output and this is the Q prime output. Take note as well of the assignments of the inputs and outputs as they cannot be interchanged. This here represents the block diagram of an SR latch using NAND gates. Let's try to see how the latch behaves using this truth table. Let's examine its behavior according to each input-output combination. For the first set of input combination, here we can see that when the present SR inputs are 0, 0, the next value of Q will always be 1, but so is Q next prime. That will happen regardless of the present value of Q. These two should never be the same, but in this case they are both 1, and that's why this is considered as an invalid or indeterminate behavior for an SR latch. Here we can see that when the present SR inputs are 0, 1, the next value of Q will always be 1, regardless of its present value as shown here by X. If Q is 0, Q next will become 1. If Q is 1, Q next will remain 1. This behavior of the SR latch is again called set, since the present value of Q is always set to 1 on its next value. Qnext prime is simply the complement of Qnext for this input-output behavior. Here, we can see that when the present SR inputs are 1, 0, the next value of Q will always be 0 regardless of its present value, as shown here by X. If Q is 0, Qnext will remain 0. If Q is 1, Qnext will become 0. This behavior of the SR latch is called reset, since the present value of Q is always reset to 0 on its next value. Again, Qnext prime is simply the complement of Qnext. Here we shall consider these two input-output combinations together since they behave in the same manner. Here we can see that when the present SR inputs are 1, 1, the next value of Q will not change based on its present value as seen here. 0 will remain 0, and 1 will remain 1. Again, this behavior of the SR latch is called no change, since the present values of Q does not change on its next value. Again, for this case, Qnext prime is simply the complement of Qnext. Here we have a variation for the circuit implementation of an SR latch. The circuit shown here is an SR latch with control input. The control input is specified by this additional input E. What it does is simply enable or disable the circuit. It can be seen in this function table that when E is 0, the circuit is disabled, so regardless of the present values of inputs S and R, the next value of Q or its next state will remain the same with respect to its present value or state. The behavior will simply perform a no change operation since the circuit is disabled. However, when E is 1, as shown here, the circuit is now enabled. The circuit will simply perform the natural behavior of an SR latch as discussed earlier and can be seen here in this part of the function table. Here is another variation for the circuit implementation of an SR latch. The circuit shown here is still an SR latch with control input. The control input is again specified by this additional input E, which is the same as the previous example and behaves in the exact same manner as the previous circuit. And it can be shown by this function table, which describes the same behavior with the previous example. The next type of latch is the D latch. A D latch circuit can be achieved using the NAND and NOR implementations of the cascaded NOT gates we derived earlier. We can do that by connecting them like this and like this. For both implementations, D is considered as the input and Q and Q prime are the outputs. Take note of where the complemented and uncomplemented D inputs are, since they cannot be interchanged. This here represents the block diagram of a D latch. Let's try to see how the D latch behaves using this truth table. You will see that when the input D is 0, the next value of Q is 0, regardless of its present value. So what that means is, if Q is 0, its next value will remain 0. If Q is 1, its next value will become 0. You will also see that when the input D is 1, the next value of Q is 1, regardless of its present value. So what that means is, when Q is 0 presently, its next value will become 1. If it is 1, its next value will remain 1. Simply, what the D latch does is show on the next value of Q whatever the present value of the input D is. So as you can see, the input D value is simply reflected on the next value of Q. If input D is 0, the next value of Q is 0. If D input is 1, the next value of Q is 1. Q next prime is simply the complement of Q next. Here we have a variation for the circuit implementation of a D latch with control input. The control input is specified by this additional input E. What it does is simply enable or disable the circuit. It can be seen in this function table that when E is 0, the circuit is disabled. So regardless of the present value of the input D, the next value of Q, or its next state, will remain the same with respect to its present value or state. The behavior will simply perform a no change operation since the circuit is disabled. However, when E is 1, the circuit is now enabled. As seen here, the circuit will perform the natural behavior of a D latch as discussed previously, and it can be seen on this part of the function table. If you can recall, in the earlier parts of this discussion, it was said that latches are level sensitive with respect to clock input signals. If a clock was used to trigger a latch, it will most likely be connected to the enable pin or E pin, which is controlled by either 1 or 0, which satisfies the latch characteristic of being level sensitive. This is also true for the previous examples of latches with enable or E input as discussed earlier. So that ends this lecture. Thank you for watching and listening, and have a good day.